Let us move on to the principle and algorithm of the Hamming code. We'll use illustrations to simplify the matter. The idea is to add other bits to the information bits, and that's the idea of the Hamming code and of any code, by the way. For example, we take the same signal, which is the following: 11 bits, and we add 4 bits, and we call this redundancy. Now we have 15 bits, and we'll put the information bits and the redundancy bits together, but in a special order. We'll do it now together. So at position 1, we'll put 1 redundancy bit. At position 2, we'll put also another redundancy bit, not an information bit. And in general, at all positions which are power of 2, we put redundancy bits. Now, in the rest of positions, we'll put information bits. So, at position 4 and also at position 8, we have redundancy bits. Now, what about information bits? We'll put them in the rest of positions. So this 0 comes here. That's the first opportunity to put an information bit. The next one should be at position 5. We don't have any choice. The next one should be at position 6, then 7. And all information bits are put at positions which are not power of 2. If we finish all of them in the same way. Now we have a new sequence of bits, but we have unknown bits which are represented by x, 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 x. We'll follow the following scheme. We select some positions. We start by position 1. We select 1 and jump over 1. Select 1, jump over 1. Select 1, jump over 1 until the end. So we selected some bits, and the addition of the selected bits should give an even value. So here we have x plus 0, which I selected, plus 0, which I selected, plus another 0, plus 0, plus 0, plus I'm adding all selected bits. And this should make an addition which is even. In order to do so, x plus 0 plus 0 plus 0 plus 0 plus 1 plus 0, in order to have it even, x should be 1. So I replace x by 1. And then do the same scheme with the second bit, which is at position 2. The scheme is the following. It is at position 2. I start by 2, select 2, and jump over 2. So select 2 bits here, jump over 2 bits, and select 2 others, jump over 2 bits, and select 2 others, and that's it. And it should be even, the same technique. All what is selected should be summed together and gives an even value. Added together. X should be also 1 in order to have an addition which is 4. And then I replace the x by 1. Then go to the bit at position 4. You can guess the technique. So 4, start by 4, select 4, jump over 4. So I select 4 bits starting by 4, jump over 4, and select an additional set of 4 bits. And the same technique, x plus all what is selected should give an even value. This is only possible if x is 0. So I replace this x by 0. And then do the same technique with 8. So start by 8, select 8, jump over 8. and it should give an even value. When I say jump over, it means when possible. If I don't have any bits, so I stop. And it gives also a value which is 0. So that's a new sequence of bits, and that's the sequence that should be sent into the channel. So I implement a real signal, for example, light or voltage, and then send this in the channel. That's the Hamming code. It's not complicated. It's very clever. So it goes out from the other side. Now, why should I do all of this? The objective is to correct the situation when there is an error. What happens if there is an error? Let us see this situation. So we have the positions 1 to 15. That's the input signal that I sent into the optical fiber in the channel. It went out from the other extremity. It gives me something deformed, which is not like the initial one. That's the received signal. I will perform thresholding, and if I perform thresholding, I will not obtain 1 at this position but 0, because the values here are low. So there is an error. There is an error here. And now I do the same scheme. Select 1, jump over 1, then start by 2, select 2, jump over 2, the same thing, and it should give even values. So for the redundancy bit at position 1, I have to do this checking for 2, for 4, for 8, for all redundancy bit positions. All additions should be even. For 1, if I calculate what is selected for 1, it gives me something even is fine. Now for 2, I know we can do it together. So for example, 1 plus 0 plus 1, it gives 2, plus 0, still 2, plus 1, 3, plus 0, 3, plus 0, plus 0. 3 is not even, so it's not good. So for position 2, the situation is bad. I put it aside. 2 is here on the left. Now for 4, I do the same technique. It is bad. It's not even. It is odd. For 8, also odd. And then I sum up all these bad positions for which the addition is not even. It gives me 14. So 14 is the position of the incorrect bit. So I located the error. It's very easy. I received 0. I switch it into 1. I have to swap it, and that's it. Why? Because it is a binary system. If the 0 value is wrong, means the 1 value is good, is right. If I have a ternary system, for example, 0, 1, 2, I cannot do this, because if the value 2 is wrong, I cannot decide between 0 and 1. But for a binary system, I can do it. So this is one of the advantages of the binary system. So that's the Hamming code, and that's the interest of the Hamming code. We'll have 2 exercises to understand in depth how it works for 1 error and also for 2 errors. This will be done in the next 2 chapters. So I replace this value by 1.